In this lecture, we're going to start looking at the very basics of how we analyze trusses in statics. And so far, we've been working mainly with balancing forces, balancing moments, things like that. And that's the foundation of the way we analyze trusses. We're still going to be taking advantage of those three equations we have, where we sum all the forces in the x direction, sum all the forces in the y direction, and we sum all of the moments about a point of reference. And so first of all, though, to talk about what a truss is and what a truss isn't, trusses are mainly they're systems of individual members that are made up of triangles. That's pretty much as basic an explanation as you can get. And here you can see, a little bitty truss that I made to kind of illustrate this purpose or this definition. This small truss is made up of all separate members that are just connected at their endpoints, and it all makes up a system of triangles. The only way you can have a truss is to have a system of triangles. If it doesn't have that, if it isn't made up of triangles, it's not technically a truss. But you can see here that even though these are made of individual members, the fact that they're bound into several triangles makes this system rigid. In fact, if I let it sit on two supports, it spans these two supports, and I can apply a vertical load, and that the vertical load that I'm applying is transferred to these two supports on either end of the truss. And so even though these are all made of this is made up of all individual free members, once I bind them all into a system of triangles, the whole thing becomes rigid. And also, because we can bind it into a system of triangles, we can now analyze the forces at each point and figure out, if I apply a force here, what will my resulting forces be in each of these members throughout the truss. Because if you apply a downward force here, which it keeps slipping off of my supports, if you apply a downward force at the top here, then let's say this is 100 pounds that I'm applying at the top. In fact, let me get my other little visual aid. This is my Forceinator 3000, patent pending. This is my force that I'm going to apply here. Well, this force is going to be counteracted, since it's directly in the center and my truss is symmetrical. This is going to be counteracted by two forces acting in the opposite direction at my supports. And so if this is 500 pounds up here, since it's centered and since this is all symmetrical, I'll have two 250-pound forces supporting at the bottom. So that force divided by 2. And now if we were to isolate just this joint right here and look at it, we have, let's go ahead and isolate it. Okay, so I'm going to kind of put my hand over there. Let me get something to cover the rest of it with, just for illustrative purposes. So I'm going to cover the rest of it with a pair of note cards, and we're just going to look at this joint right here. Since I have a reaction force of 250 pounds, I can now analyze this point, and I can say, well, if I have 250 pounds in the vertical direction, that has to be resisted by the vertical component of the force going in this direction. In fact, let me get another one. Here's an even bigger force. Okay, so something has to counteract that force. It would be the vertical component of whatever force is in this diagonal member here. So once we do that, we can tell, okay, if we have a force here and we have a force here, well, this force has a horizontal component. So the horizontal component of this force has to be counteracted by some force in this horizontal member, whether it pushes this way or whether it pushes this way. And as we move along our truss, once we've figured out these two forces, we can move on to the next joint, and we can say, well, we have, we know what our force is in this member. We can find out what our forces are in these two members, and we can go on through the rest of the truss. So going back to that basic definition of a truss that we talked about, trusses are just a structural system made up of several elements that form triangles. They take applied forces and redirect them along the components of a truss as tension and compression. So, if I apply a force here, this force is quickly spread out over all the members that are attached to that joint. And then as those forces propagate through those members, they again spread a component of them to to the secondary members that those attach to, and so on and so forth, until you finally get down to your reactions at your supports. And then at the end, when you look at the whole thing and you sum all of your tension and compression forces and all your members, they're all going to be equal to 0 because everything's static. Okay, so there's a couple assumptions that are used in our analysis of trusses. Your book goes through a couple. I'm going to kind of paraphrase them a little bit. One is that all the members in your truss are straight. That's very important because all of the forces in your trusses are resolved into tension and compression. So if you have a member that's bent, you no longer have pure compression in this member. If it's bent, you have some sort of bending moment that's introduced into this member instead of being just purely in compression. So we're assuming that all the members in whatever truss we analyze are straight. We're assuming that every joint is held together by a pin. So you can see these little machine screws I have here. All that means is that if we were to look at a joint just by itself, that pin is not restraining any rotation. So there's no stiffness with regards to rotation. Each joint is free to rotate about the pin that is attached to. And that's very key, because if we have, for instance, if we were to have a member like this where there's a slight overlap, and we were to put two pins in it, this no longer acts like a pinned connection, because any force that I place on this it has to be resisted in terms of shear and bending and stuff like that in the screws. So this joint is not freely rotating; it's bound, and so that's not what we would consider in a true truss. So the next one is, we're going to neglect the weight of the truss. The forces that we're going to be supporting by our truss are going to be so much more than the weight of the truss itself. So by comparison, that is. So we're going to, for the most part, neglect the weight of the truss. And also, we're going to assume in truss analysis that loads are only applied at the pins. Okay, so we're not applying a force right here. We're not applying a force right here in the middle. We'll get into that in a later lecture. But for right now, we're assuming that any force we have is going to be applied directly to a pin. And then, as always, our fundamental assumptions on which everything in statics is based. The sum of the forces in the x direction is equal to 0. The sum of the forces in the y direction are equal to 0, and the sum of the moments about any given point of reference is always going to be equal to 0 as well. So that's an introduction on what a truss is and our assumptions going into our analysis of trusses. Next video we'll start to look at some simple examples.